In this chapter, we want to just cover some basic number theory theorems and some proofs, and which is developed by Euclid, and the main concepts is from him. Okay? So the definition of divisor and divisibility and multiple factors divisors is as the following. Let's say a is a non-integer, non-zero integer. Okay, so it could be positive, negative integers, and b could be any integer, and including zero. Then when you say a divides b, it can be written by like this as a mathematical symbol. If there is a corresponding integer q satisfying that equation. So the meaning is a becomes a factor of a b. We say that, right? A is a factor of b. And at the same time, of course, q is also a factor of b, right? But mainly the given two numbers are a and b. And if the relation is like b can be written by multiple of a by a certain integer q, then b is a multiple of a, and a is a factor of b, and we say a divides b and written that way. So from now on, whenever we see a divides b and vice versa, then we always have there is an integer, right? Q such that b can be written by q times a. Okay? Remember those, and q should be an integer. And for the proof, because it takes long to write all things, we made some kind of symbol. So there is or there exists. It's just kind of flipped shape of capital E, right? So it came from there exists. Okay? So use that one. So there is an integer G or Q in this case, such that same like that. Right? And even for there is an integer, and the natural number or positive integer set is like that, and boldface Z is for integer set, right? So more simpler notation is there is Q in the integer set, okay? And such that B equals Q times A. So most likely we are going to use this kind of writing, okay? But the meanings are like this. Okay, so if we want to say A is non-zero integer, then we can say that like A is an element of integer set except 0, right? Okay, so right now, the only definition or only formula we have is when A is a divisor of B or B is a multiple of A, then we should have an integer satisfying that equality. That's all. Now, using that definition, let's just try to prove a certain fact. A is a divisor of negative A. Okay, of course, A is still non-zero integer, just any integer except 0. So A could be negative. So negative A means positive. But doesn't matter, right? Which one we have. We want to show this. So temporarily, just imagine that is a B, right? Then we want to show this, right? This is a conclusion, which means we need to show or we need to find some integer having that. Okay? And that integer must be an integer, right? So you have to mention that one. So we can say since -1 is an integer, right? And it's satisfying that a times -1 becomes negative a, which is b, right? So b equals that q times a. That's what we have, right? Therefore, we can say A is a divisor of negative A. Then, by the same kind of similar style, A is a divisor of A. You can do that, right? It's almost a copy of this one. Slight difference on Q. And how about 1 is divisor of A? Since we already know A itself is an integer, cannot be 0, but we know it's an integer, right? And what this satisfying is when we multiply A to 1, we got A, right? So temporarily, you can think that is for A, right? And that is for this portion, and this one is for Q, right? Placed in Q part. So because of that, we get 1 is a divisor of A, right? By the definition, once again. So as you can see here, all we need is just looking for an integer. That's all. So for this case, key point is, yeah, we want to see there is an integer, right? So we want to show at the end such that the 0, the B, is some Q times A, right? Then what number makes this multiplication become 0 for any non-zero? A is not 0, right? So the only number should be 0 there. And 0 is an integer. So we can say since 0 is an integer, okay, and such that this way, right? Therefore, we get that A is a divisor of 0, the B. Okay? So when you compare this with the other case, it's just same thing, right? You're just looking for an integer and satisfying that equality, always like that. Now next one is a little bit complicated. Okay? And another thing is the statement has if and only if, which means in math, whenever you have P implies Q, the meaning is if P is satisfied, then Q is what we get, okay, as a conclusion. So it's a conditional statement. Then P if and only if can be written by this way. So P if and only if Q, right? Which means P implies Q and Q implies P. Okay? So this statement is actually consists of two different conditional statements, which means the proof of that statement requires proof of two statements, right? Unless you can do it all together at once. Okay, so you have to separate into two parts, 1 and 2, for most like this kind of if and only if statement. Okay? So first, let the given condition, right, is A is a divisor B and B is a divisor of A. You just accept that condition and try to get this outcome at the end. Right? Then from there, by the definition, A is a divisor of B means there is an integer, right? So let's say it's Q in the integer set such that the relation should be B equals Q times A, right? But from the second one, B is a divisor of A. So there must be another integer satisfying A equals that P times B. Of course, respectively, but anyway, because we are accepting these two conditions means there must two integers. They might be same number. There's no conditions whatsoever, just integers enough. So there must be two integers satisfying these two equalities, right? So let's just try to put these together. So instead of B, let's just substitute by Q times A. Then from there we have A equals P times B, which is P times Q times A, right? So it's PQ times A. Now the condition was those PQs are integers. And right now A equals PQ times A. So that means PQ must be 1, right? There's no other way. So if PQs are integers and the product of those two numbers equals 1, then there is no other way unless that we have the PQs are both 1s or PQs are both negative 1s, right? There is no 1/2, 1/3 are possible for P and Q, right? They're integers. So these are only two cases. Hence, if the first case, if P, Qs are 1s, then when you look at those together, we have A equals B, right? And if P, Qs are negative 1s, then A equals negative B and B is negative A at the same time, like that, right? So all together, that notation is therefore, right? Like the vertices of triangle shape. The meaning is therefore. So therefore, altogether, A, the absolute value of A is same as absolute value of B. Now, let's do the second part. We just finished the first case. So in the converse one, our assumption is A, the absolute value of A and equals absolute value of B. Which means what? A must be plus minus B. That means A equals 1 times B or A equals, okay, and at the same time, right? A equals negative 1 times B. So that means from here, we found an integer having those relations. So B must be a divisor of A, right? But at the same time, you can change that one to the other way, right? Okay, and even this one to the other way. So B must be also a divisor. I mean A, because you can think that one as B equals negative 1 times A too, right? So A is a divisor of B. You can conclude that. So that's the end of proof. Next one, same thing, right? So let me give you this one. So let A is a divisor of 1. That means there is an integer satisfying that 1 equals A times, I mean Q times A in that order. Just keep that. But when you start it, A is a non-zero integer, right? And Q is an integer. So when you multiply two integers together, make it 1, which means A equals like two different cases, either A equals 1 and Q equals 1, or A equals negative 1 and Q equals negative 1 at the same time, right? So anyway, which means what? A equals 1 or A equals negative 1. Okay, the reverse one, you can start with whether a equals 1 or a equals negative 1. So please do separate cases, right? It's very simple, right? So please finish this proof by yourself. Okay, let's do the following ones. Okay, it's not moving right now. Okay, next one. A is a divisor of B and B is not 0. And remember that A is also not 0. Okay? Then the absolute value of A must be smaller than or equal to the absolute value of B. So let's start proving it. So starting is the proof, the mathematical proof consists of three parts. The first one is hypothesis. The second part is body, which means all the collection of these arguments. And the third part is the conclusion. So you just restate the conclusion, something like that, right? So always you have to start with the hypothesis, which is A is a divisor of B and B is not 0. And the conclusion is what? Therefore, A is less than equal to B, like that. So that's what we are looking for at the end. But from here, let's just use this concept here first. Then, because of that, there is an integer satisfying B is Q times A. Right? Now, the given condition was in the beginning, A is a non-zero, right? And because of that, B is also not 0. So when you multiply those two numbers and makes B, then look at the case. Of course, A and Q, B, all of them can be positive or negatives. But when we think the absolute values of each, then each number is greater than equal to 1 for absolute values, right? So because of this condition, we know that the absolute value of A is greater than equal to 1, right? And absolute value of B is greater than equal to 1. So Q can be negative, of course, but if Q, absolute value of Q should be greater than equal to 0, that's possible, but what happens if Q equals 0? Then 0 times A becomes some number which is not 0. No way, right? Which means what? Q cannot be 0, right? So meaning is Q, the absolute value of Q must be also greater than equal to 1, right? So altogether, absolute value of Q must be greater than equal to 1. Then, therefore, we can say the absolute value of B equals absolute value of Q times, actually entirely Q times A, right? But we can separate that one into the product of two absolute values. And because Q is greater than equal to 1, that right hand side is greater than equal to 1 times absolute value of A, which is absolute value of A. So now we just show absolute value of B is greater than equal to absolute value of A. Okay. Therefore, finally we can say that conclusion. Okay, so that's the end of proof. Okay, let's look at the next one. A is a divisor of B and divisor of C at the same time. Then A is a divisor of the combination of A and B by plus or minus. Okay? So let me just show the first case, and you do the second case. Okay? So let A is a divisor of B and A is a divisor of C. Then altogether, we already did this one. There are two integers, let's say Q and P, such that B is a Q times A and C is a Q times P times A, right? Together. Then we want to see the relation between A and B plus C. So let's just add these two. Okay? B plus C can be written by Q times A plus P times A, which can be written by Q plus P times A. Now, these P and Q's are integers, right? Therefore, P plus Q is also an integer, right? So you can restate that one by T or S, whatever, as one integer, right? But it's okay, right? We know this P plus Q itself is an integer. Therefore, when you look at this as a one number and that as a one integer and A, then because of that, you can say A is a divisor of B plus C. So you have to redo everything by yourself, right? But please include the proof of second part, which is exact repeat of very similar each other, right? Only small differences. Okay, next one. The condition is A is a divisor of B, then A should be a divisor of K times B for any integer K, no matter what, even including 0, right? So let's start with writing down the hypothesis. Is what? Let A is a divisor of B. Then from that given hypothesis, we can say there is an integer Q such that B equals Q times A. Now we want to compare the relation between K times B and A, right? So let's start with K times B. So that for any integer, so let me just write down that. For any integer K, K times B is also an integer, right? Okay. So we don't need to mention that, but make sure that. So that can be written by K times, instead of B, we can put Q times A, right? And let's look at this one in this manner. K times Q times A, right? So that big one number equals this number times A. And what is this number, K times Q? Since K is an integer and Q is also an integer, right? We already have that and that, right? So we know KQ is also an integer, which means what? We found an integer having that equality. Therefore, we can claim A is a divisor of K times B. Okay, that's the end of proof. Okay, let's do the last one among this type of group. Okay, questions. And this is something we need for later parts in the later chapters. Okay? Let's say A is a common divisor of B and C. Okay? That's the meaning of it. Then A is a divisor of the linear combination of B and C, which means you just use any integers m and n and make this linear combination of b and c. So no matter what m and n's we are using, still a becomes a divisor of that. So that's what we want to prove here. So let's say A is a divisor of B and A is a divisor of C, which means there will be two integers, P and Q, such that B is P times A and C equals Q times A. Okay? After you found those relations, always look at the conclusion, right? We want to do this. Okay? We're looking for the relation these two numbers, between these numbers. So for any integer m and n, let's start with m times b plus n times c. Then m times b, which means p times a, and n times c. Instead of c, we could put q times a, right? Our goal is looking for the relation between that number with a, right? So let's just separate this a from there. So mp times a plus nq times a, and even we can change that onto mp plus nq times a. So this number, this is another number, right? Equals that number times a. So don't just say, oh, therefore a is a divisor of the mb plus nc. No, because you have to make sure that number is an integer, right? That's the big condition in the definition, right? of the divisor and multiples, right? So you have to show that since p, q's are already integers, right? And mn's are also integers. So these are just the product and addition of those for integers, right? So since p, q, m, n's are integers, therefore mp plus nq is also an integer. And because of that, we can claim that a is a divisor of mb plus nc.